Our first approach to building a player for small single-player games is called compulsive deliberation. It's a big name for a relatively simple concept. In compulsive deliberation, on each step, the player examines the then current game tree to determine its best move for that step, and it then makes this move. It repeats this process on the next step, and so forth until the end of the game. Now, in pure compulsive deliberation, each step of the computation is independent of every other step. No data computed during one step is accessible on subsequent steps. The player treats each step as if it were a brand new game. Now, this is obviously wasteful, but it doesn't really hurt so long as there's enough time to do the repeated calculations. We start with this method because it's simple to understand, and at the same time it serves as a template for the more sophisticated and much less wasteful methods to come. Using the basic subroutines provided in the GGP starter pack, building a compulsive deliberation player is not difficult. The implementation looks like this. As shown, it's almost identical to our implementation of legal and random players. The only difference lies in the play handler. In selecting an action, a legal player uses find legal X to compute a legal move for a given state. In compulsive deliberation, the play handler instead uses a subroutine called bestmove that does a more sophisticated computation. Before looking at bestmove, let's look at a slightly simpler subroutine called maxscore. Maxscore takes a state as argument and returns the best score that the player can obtain by any sequence of actions in the specified state. Let's see how it works. As its first step, the procedure checks whether the given state is terminal. If so, then the best possible score is a reward for the specified state. It computes this by calling the find reward subroutine on the role, the state, and the rule set. If the state's not terminal, then it tries each of the actions legal in that state. Computes the maximum score for the state that results from executing that action, and returns the best score it finds. First step in doing this is to compute a list of all legal actions. It initializes the variable score to 0, then loops over the possible actions. Since in general there can be multiple players, findX takes as arguments a list of actions of all players. In this case, we have a single-player game, so the player creates a list of just one element. The player then uses findNext to compute the next state resulting from this move in the current state. Then finds the max score for that successor state. If the result is 100, then it simply returns that value, as there's no way to get more than 100 points. Otherwise, if the result is greater than the current score, it updates the score and goes on. And finally, if it has not encountered a 100 value in the process, it returns the current score, which by construction is the maximum score for all possible actions. Okay, now that we have max score, let's return to best move. The definition uses max score and is actually quite similar to max score. There are just a few differences. First of all, best move is not itself recursive, though it calls max score, which is recursive. Best move does not need to check whether the state is terminal because it would not be called if the game were in a terminal state. That's already been checked. It initializes a variable called action to the first legal action, and it then behaves pretty much like max score, trying each possible action to see if it can find one with a higher score than any previous action it has seen. If it ever encounters a max score of 100, it simply returns the corresponding action. Otherwise, it proceeds until it has tried all actions, at which point it returns the action with the highest max score that it has seen.